Okay, so histogram is given by HRK is equal to NK. Here RK represents gray shade. So for an 8-bit image, your RK will range from 0 to 255. So for the given image, you need to count how many pixels are there belonging to say gray level 0, then gray level 1, gray level 2, up to gray level 255. And NK represents that count. How many, if your K is 255, how many pixels are there belonging to gray value 255? That is given by H of 255. Okay. So, and yeah, for an 8-bit image, there will be total 256 gray level. So your x-axis will vary from 0 to 255. Okay. And y-axis gives you respective number of pixels belonging to respective gray shade. So this is definition of histogram. Okay, so this is an example of histogram for this given image. Okay, and here instead of discrete gray values, here continuous gray values are considered, say from 0 to 1. Okay, so 0 to 1, these are gray values in a continuous range, and y-axis gives you number of pixels belonging to each gray value. Okay, now let us see what do you mean by normalized histogram. So basically normalization is useful for comparing various images. So in order to normalize the histogram, what we do, whatever counts we have derived using this equation, HRK is equal to NK, we divide this number NK by total number of pixels in the given image. So if you have say 10 by 10 as image size, total 100 pixels are there. So whatever your count for each gray value, we divide it by 100 to get normalized histogram. So dividing each of histogram at gray level RK by the total number of pixels in the image N gives you normalized histogram. And it is say denoted by PRK. Then PRK is equal to NK by N. Okay. So NK represents number of pixels belonging to kth gray shade, and it is divided by total number of pixels in the image. So basically normalized histogram PRK gives an estimate of the probability of occurrence of gray level RK. Okay, so normalized histogram is nothing but probability distribution. Okay, so and as we have normalized it, sum of all components of a normalized histogram is always equal to 1. The value given by the normalized histogram for a certain gray value can be read as the probability of randomly picking a pixel having that gray value. Okay, so we can call normalized histogram as probability distribution, and each component of normalized histogram gives us probability of occurrence of particular gray level in the given image. Okay, so now let us have a look at how the histogram is useful, what it tells about the given image. Okay, so here there are various examples of histogram. Okay, so this is a histogram which has a shape same as Gaussian distribution. I think all of you are familiar with Gaussian distribution. So this is for this particular histogram, this shape is identical to Gaussian distribution. Now from the histogram, we can get an idea about mode, mean, and median. These are some statistical parameters. So what is mode? Mode is the value that occurs most frequently in a distribution, and it is usually the highest point on the curve of histogram, right? So mode represents most frequent value, most frequent gray value in the given image. Okay, so if you consider this histogram which has Gaussian shape, this peak value gives you mode, because this is highest frequency point. So if this point, if this peak occurs at gray level X, we can say X is mode of the histogram. Okay. So it is most frequent occurring value. Then what is median? Median is the value midway in the frequency distribution. So midway means one half of the area below the distribution curve is to the right of the median, and one half of the area is to the left of the median. So again, for Gaussian distribution, as it is symmetric around center, the mode point is, median point is same as mode point, or it is the same, it is central value of this curve, because half of the area on the left exactly matches to the half of the area on the right of the central line. Okay. So this X is median for this particular histogram. Then what is mean? Mean is the arithmetic average, and it is defined as the sum of all brightness value observations divided by the number of observations. So mean is nothing but arithmetic average of all the gray values present in the given image, all the pixel values present in the given image. Now for a Gaussian distribution, your mean, median and mode, they occur at same point. Say this is X. Okay. Because of symmetrical nature of Gaussian distribution, they mean, mode, median, they are appearing at the same point. Okay. Now if you consider this particular distribution, which is known as negatively skewed distribution. Okay. Now for this distribution, of course, this mode value is say x1. Okay. So say this is your x1. X1 is mode value, because here you are getting the peak. So this is most frequently occurring gray value in the given image. So mode is here. Then median is at this point X2. Why? Because median gives midway of the total distribution. If you compare this left side area, it matches exactly with the right side for point x2. Okay, so x2 is median, and this x3 is arithmetic average of all pixel values in the given image. So if it is negatively skewed, you will get say x3 mean value here, median value here at x2, and mode is at x1. And if you look at this particular diagram, this distribution, it is known as positively skewed distribution. And here your mode, median, mean sequence is exactly opposite to that of negatively skewed distribution. So here mode is frequently occurring value. So mode appears here. So this is your mode x1. Then median is here x2, gray value x2 represents median, and x3 represents mean for positively skewed distribution. Now there is one more example here which represents uniform distribution. So can you tell me what is uniform distribution by looking at this graph? What is meaning of uniform distribution? In case of uniform distribution, frequency of occurrence of each gray value is identical. Yes, Sharon, your answer is correct. All gray levels have same number of pixels. Okay. So this is uniform distribution. Again, for uniform distribution, your mean, median, mode will appear at the same gray value, say x1, because of the symmetry of the curve. Of course, there is nothing like as mode, because every pixel, every gray value is occurring with the same frequency. Okay. So mean, mode, and median, all of them are same at say x1. Now, as compared to these other histograms, now look at this particular histogram. It is different. This is multimodal distribution. If you look here for very first histogram, there is single mode value, right? There is only one uh, gray value which is occurring uh, at say highest number of times. But if you look at this distribution, there are two mode values in this distribution, x1 and x2. Okay. So two gray levels, x1 and x2, they are occurring most frequently in this particular histogram. So there are two modes. Okay. So we can call this as bimodal histogram. Now similarly, if you have one more mode in the histogram, you can call it as multimodal histogram. There are multiple mode values. Okay. So from the histogram, we can get an overall idea of the given image. Okay. Whether the image has Gaussian distribution, or whether image has negatively skewed distribution, positively skewed distribution, or uniform, approximately uniform distribution. This idea we can get by looking at the histogram, or whether an image has multimodal histogram. Okay. So this broader information in broader sense is available by looking at the histogram of the given image. Okay. Okay. So then normalized histogram is also useful to determine statistical parameter values for the given image. Let me erase these extra characters from the screen. Okay. So mean value is, all of us know, it is arithmetic average of all the pixels values present in the image. We can also derive it from the normalized histogram. If Hg represents normalized histogram, means how we obtain normalized histogram, for every count value, we divide it by total number of pixels. So that gives us normalized histogram, say Hg. Now, from the normalized histogram, we can obtain mean value by summation G into Hg, where G represents gray level and Hg represents normalized histogram value. Okay, so for this particular example, say there are 6 different gray values, and y-axis represents normalized histogram. And as this is normalized, we are getting values less than 1. Okay, if you look at y-axis, these are not counts as numbers, but these are discrete value. These are values between, fractional values between 0 to 1, because we have divided each count by total number of pixels. So for say gray level 1, if normalized histogram value is 0.3, for 2 it is 0.1, and so on. So if we multiply gray value 1 by its normalized histogram, then multiply 2 by its normalized histogram, that is 2 into 0.1, 3 into 0.2, 4 into 0.1, and so on. And if we add all these numbers, it gives us mean value of the given image. So for this example, mean value is 2.6. So this is average gray value for the given example. Okay. So mean value is the average gray value of the image, and it tells about the overall brightness appearance of the given image. So we can also determine variance from the normalized histogram. So this is a mathematical equation to determine variance. Again, Hg is normalized histogram. Now here M indicates mean value, which we have derived using this equation. Okay, so basically summation G into G minus M square into HG, it gives us variance of the image. Okay, and what is physical significance of variance? Variance gives us a measure about the distribution of the histogram values around the mean. How your pixel values are distributed around the mean, that is indicated by variance. Okay, so this is how we can determine variance from normalized histogram. And square root of variance gives us standard deviation. So the standard deviation is a value on the gray level axis showing the average distance of all pixels to the mean. So here for standard deviation, unit is same as your pixel value or mean. If we consider variance, it is square of the uh, square, it is in square format, so its unit is different, it is square unit square, right? So to get the original unit, we can take square root of variance, that is nothing but standard deviation. So basically standard deviation gives you an idea about average distance of all pixels to with respect to the mean value. Okay, so higher the variance, higher the standard deviation, of course, and higher the variance indicates higher the image's contrast. Contrast value is greater. Lower the variance, lower the contrast. So here is one example. For very first image, mean value is 0.73 and standard deviation is 0.32. For second image, mean value is 0.71 and standard deviation value is 0.27. So this second image has lesser amount of standard deviation and hence contrast is less as compared to first image. Okay, now let us have a look at what do you mean by dynamic range and contrast of the image and how histogram is useful to tell about contrast of the image. So as the name indicates, this dynamic range is basically a property of measuring device. So if we are using a camera to capture that image, then dynamic range is a parameter which is related to camera, and contrast is a property of the signal captured, or it is property of the image which is captured from the camera. Okay, so dynamic range is a property of measuring device, while contrast is a property of the signal measures, assuming it is within the dynamic range of the measuring device. So dynamic range refers to the difference between the brightest and the darkest objects that the camera can capture. Okay, so we can have particular dynamic range for the given camera. Okay, and this dynamic range is nothing but difference between the brightest and the darkest level the camera can capture. And what is contrast? Contrast is difference between high and low value of the captured image. Okay, so a high contrast image has pixels spread out towards the high and low ends of the histogram. So contrast is a parameter related to captured image, and dynamic range is a parameter related to the image capturing device. So this is an example. This is high contrast image. This is low contrast image. Why? In this case, you have, if you determine difference between, say, darkest point and brightest point, this difference is greater for this image than this image. Here, difference between darkest and brightest level is almost zero. If you look at this image, there is only one gray value appearing over the entire image, or there is very small difference between darkest and brightest point in the given image. So this image is an example of low contrast image, and this is an example of high contrast image. So a camera with a very large dynamic range will be able to capture images with high contrast, but the two are not necessarily directly connected. Okay. So dynamic range is related to capturing device, and contrast is related to captured image data. Okay, so for example, you could get a very low contrast image even from a high dynamic range camera. Because if your source itself, if it has very less number of, if it has low contrast, even with high dynamic range camera, you can get low contrast image. But if your source itself has high contrast, your camera with high dynamic range can capture that high contrast image. And if you consider reverse case, say your environment is very ideal, means your say your object is properly illuminated, and if the source contains all possible uh, pixel values, it means your source has good contrast. But if you have a camera with low dynamic range, in that case it is not possible to get that high contrast image because of the limitation of your capturing device. If your camera has low contrast, low dynamic range, it cannot capture high contrast images. Okay. So basically this is difference between dynamic range and contrast. Hope you are getting the difference. So say you are having a camera with dynamic range, which is measured by, which is given by 0 to 255. Say if your camera is representing images in terms of 8 bits, its dynamic range, we can say it is from 0 to 255. Okay. And if by using this particular camera, say we are capturing two different scenes. Okay, in one scene you have captured range between 4 to 232, and in other scene you have pixel value range from 120 to 130. Okay, so we are using a camera with dynamic range 0 to 255. For one scene range is 4 to 232, and for other scene range is 120 to 130. So out of these two scenes, first image has high contrast. Why? Because the ratio between high value and low value is large. Or we can say difference between highest captured value and lowest captured value is large. That's why we can say scene 1 has higher contrast than scene 2. If you look at scene 2, for scene 2 or for image 2, difference between lowest and highest pixel value is very less. It is only 10 difference between these two. Whereas for first scene, this difference is very large. Okay. So we can say that first image or first scene is high contrast image, while the second image has low contrast because the range is very small. Difference between darkest and brightest pixel is very small. Okay, so this is meaning of contrast. Now let us see how histogram is useful to get an idea about contrast. Now, if you look at this image, this might be an image which is captured in dark. And that's why if you look at the histogram, total range for the histogram is 0 to 1. Okay, if we consider continuous gray values. Okay, and out of this total range 0 to 1, your input image has image is distributed over 1/3 of the available range, right? All your pixels are very dark and they are taking values between say 0 to 0.3. Okay, available range is 0 to 1, but your input image has distribution between 0 to zero point 0.3. So we can call this image as low contrast image, or if you look at the image, we can say this is dark image, and histogram is concentrated only in the lower one-third portion of the total available range. Okay. So for the given image, dynamic range is 0 to 1, but the contrast is poor. Contrast is 0.3 minus 0, that is approximately 0.3. Contrast is low. This is an example of dark image, and it is also a low contrast image. Now, if you look at this image, this is an image which is say captured in very bright light, and that's why if you look at the histogram, your total available range is 0 to 1, but your image is concentrated only in the on the brighter side of the total range. It is taking values say ranging from 0.5 to 1. Okay. So this is also an example of low contrast image. Okay. So this is a bright image, and here all the gray values are concentrated on the upper portion of the histogram between 0.5 to 1. It does not occupy total dynamic range available from 0 to 1, but it is concentrated only on the brighter portion of the histogram. Okay. So this is also an example of low contrast image. And now if you look at this image and if you observe the histogram, how it is different than previous two images. This first image was concentrated in the lower portion. This second image was concentrated in the upper portion. And this last image, it is, if you look at the histogram, this histogram is distributed equally over the entire available range from 0 to 1. That's why we can say, by looking at the histogram, we can say that this is an image with very good contrast, right? And if you look at the image, you can justify this statement, right? If visually we can say this image has very good contrast. And if you look at the histogram is distributed approximately equally over available dynamic range, which is from 0 to 1. Okay. And that's why histogram is that's why contrast is very good for this particular image. So these are the three pictures of same object which are captured in different illumination conditions. First is an image with poor light, which is captured in poor light. This is, and that's why contrast is poor. Second image is captured by over illuminating the object, and that's why a contrast is again poor. It is appearing as bright image, and this particular image is captured with very good illumination, and contrast for this image is very good. If you look at the histogram is approximately equally distributed over available dynamic range. Okay, so I think you are getting the concept of contrast and how histogram helps in identifying contrast of the image. If you have any doubt, please type in the chat box. Okay. Okay, so once again, these pictures are shown here. So for very first image, component of histogram are concentrated on the low side of the grayscale. And for second image, component of histogram are concentrated on high side of the grayscale. And for both these images, contrast is poor. Again, there is one more example for this particular image. Here, histogram is narrow and centered toward the middle of the grayscale. If you look at the histogram is concentrated in the middle portion. Again, this is an example of low contrast image. And this last one is an example of good contrast image. Here, histogram covers broad range of the grayscale and the distribution of pixels is not too far from uniform. We can say it is approximately uniform distribution. Of course, there are few peaks, vertical lines in the lower portion. These are because of the black background in the image. These peaks are there. But if you look at overall nature of the histogram, it is approximately uniform. Okay. So your histogram, uniform histogram plays an important role in case of images. If histogram is uniform, we can say image has very good contrast. Okay. So now if we have say captured this image or this image or this image, now by can we have some image processing technique which will convert captured image from low contrast to high contrast image. Okay, so yes, such technique is available and this technique is known as histogram equalization. Now, if we have uniform histogram, we can get good contrast image. So because of some flaws in image capturing environment or image capturing device, if we get an image with low contrast, by modifying histogram of the captured image, we can try to achieve good contrast image. And this technique is known as histogram equalization. Why it is known as histogram equalization? Because say if your captured image has low contrast, your histogram is concentrated in certain range. And by applying histogram equalization, we try to spread this histogram approximately equally over available dynamic range. Okay. And when the histogram becomes approximately uniform, we get a good contrast image. Okay. So in order to convert your low contrast image to good contrast image, we can process histogram of the image so that we get approximately equal distribution of gray values. Okay. Now let us have a look at how this histogram equalization works. Okay. So as the low contrast images histogram is narrow and centered toward the middle of the grayscale, if we distribute the histogram to a wider range, the quality of image will be improved. Quality in what sense? Basically, contrast of the image will be improved. And we can do it by adjusting the probability density function of original histogram of the image so that the probability spread equally. Okay, so an output image is obtained by mapping each pixel with level RK in the input image into a corresponding pixel with level SK in the output image. So let us consider now instead of considering discrete signal, let us consider that your image intensity values are varying between a continuous range between 0 to 1. Then we want to apply a function t on the original gray value r to get new gray value s. Okay, and this transformation function we are applying for equalizing the histogram. Okay, so let us say this t is the transformation on original gray value r and r is continuous in nature. It is varying between 0 to 1. Then this transformation t satisfies basically these two conditions. First condition is TR is single valued and monotonically increasing in the interval 0 to 1. And this TR, another property of this function is if your R is in the range 0 to 1, S is also in the range 0 to 1. Okay. So T of R, that is S, it is also in the range 0 to 1. So what is use of these assumptions or these conditions? When your function t is single valued, it guarantees inverse transformation. There is one-to-one mapping, so you can inverse transform this S and you can get original value R. Okay, and because of monotonicity, it preserves the increasing order from black to white. Okay, so because of single valued and monotonicity, we can guarantee inverse transformation. And this second condition guarantees that output gray levels will be in the same range as the input gray levels. Okay. So these are the two properties or conditions for this transformation function T. Okay. And because of these conditions, we can easily determine R by applying inverse transformation on S. Now, let us see how we can get the equalization. Okay. So this transformation function TR is given by integral 0 to R PR omega d omega. Okay. So this is your histogram equalization function. Okay. So this is nothing but cumulative distribution function. This integration 0 to particular gray value R, it is that we can achieve by integration till this particular value, integration of all probability values till gray value R. Okay, so this is your histogram equalization function. Now let us see whether this transformation really gives you equalization or not. Okay, so this integral 0 to R PR omega d omega. So here this omega is dummy variable and R represents gray value which is continuous in nature between 0 to R, and PRR, it denotes continuous probability density function of gray levels of input image. Okay. Now, if your transformation satisfies these two conditions, then this as per probability theory, this equation is true. PSS, that is probability density function of modified gray levels, PSS is equal to PRR into DR by DS. By probability theory, this equation is true. Okay. Now we have now this integration function integral 0 to R PR omega d omega gives us histogram equalization. Now to prove that this gives us histogram equalization, let us first differentiate this equation with respect to R. So on this side we will get ds by dr, and differentiation followed by integration means your integration is cancelled and you will simply get PRR on this right side, right? Okay. So we differentiate S with respect to R on both sides of this equation. So we get ds by dr is equal to PRR. Okay. And this now simply substitute this equation 1 in this particular equation. Substitute ds by dr from equation 1. So we get here PSS is equal to PRR into 1 upon PRR. And so here PRR is cancelled with this and we get PSS is equal to 1. And what is meaning of PSS is equal to 1? It means it is nothing but your uniform distribution. Okay, so the PSS represents equalized histogram. So this proves that This cumulative distribution function is useful to equalize histogram of the given image. Okay. So though this is mathematically complex, with one example we can uh, understand this histogram equalization process. So for that, just let us have a look at discrete equivalent of this equation. So what is discrete equivalent of integration? It is nothing but summation. So the same equation in discrete form we can write as shown here. Sk, that is modified gray value, is given by T of Rk, and now T is replaced by summation. Your integration is now replaced by summation PRRJ, where J runs from 0 to K, and K can take any value between 0 to L minus 1. So for an 8-bit image, K can range from 0 to 255, and your histogram equalized gray value Sk is nothing but summation of PRRJ, where PRRJ is given by Nj divided by N, which is nothing but normalized histogram for gray level J. Okay, so we can achieve histogram equalization, or we can get processed gray value Sk simply by cumulative addition of normalized histogram values. Okay, so Sk is given by summation Nj by N. Okay, and your J runs from 0 to K. Okay. So these are your images before histogram equalization. When we apply this cumulative, when we apply histogram equalization on left side images, we get these output images, and here we can observe that these resultant image has very good contrast as compared to original image. And if you look at the histogram of equalized image, you can observe that previously original histogram was concentrated in lower 1/3 portion of the histogram, but if you look at resultant histogram, it is distributed over entire available range. Similarly, for this image, here original histogram was concentrated in upper 1/3 portion of the image, and after histogram equalization, it is spread over entire dynamic range approximately equally, and its resultant effect is contrast of the resultant image is improved. Okay, now if you shall we continue with this in the next lecture with actual numerical, you will find it easy how to equalize the histogram. It's shall I continue, or shall I continue it in the next lecture? Okay, so I will continue with the numerical in the next lecture. Now I request all of you to type 5 digits of your PRN number followed by your name. Don't put any dash or comma or anything between your PRN number and name. Simply type PRN number space and name. Thank you all. If you have any doubt, please ask. Please type it in the chat box.